going to be going over molecular geometry in chemistry. So in this video, we're going to be going over bonding, electronegativity, the VSEPR theory, polarity, and intermolecular forces. So the first thing we're going to be going over is bonding and electronegativity. So here's a quick review of bonding. There's metallic bonds, ionic bonds, and covalent bonds. Metallic bonds are between metals and metals. Ionic bonds are between metals and nonmetals, or cations and anions. And covalent bonds are between nonmetals and nonmetals, or you could say two anions. So here are some properties of each bond type. Okay, and here's a visual of each chemical bond. So there's ionic bonds, which over here you can see how in an ionic bond, there's a donating and gaining of electrons, whereas in a covalent bond, there's sharing of electrons. And then metallic bonds is when electrons can freely move between metal ions. So that's called a sea of electrons. Okay, so electronegativity, what is it? So electronegativity is the tendency or the ability of an atom to attract electrons to itself in a bond. So I think in one of the earlier units, we learned how to, like the periodic trend for electronegativity. So we know that electronegativity decreases down and increases across. We'll go over that a bit more. But the most electronegative element will attract the electrons to itself. So basically electronegativity is just like an element's ability to attract electrons to itself. So electronegativity is what causes the unequal sharing of electrons between bonding. And so this is where polar and nonpolar covalent bonds come from. So here's the electronegativity trend. You'll notice that electronegativity decreases down a column and increases across the period. So the most electronegative element is fluorine. So the more electronegative elements are the ones over here. Okay, so let's talk about covalent bonds. So we know that covalent bonds is when atoms share electrons. So a true nonpolar bond is when there's a covalent bond in which they're formed when two elements that are similar share electrons equally. So this means you could look at diatomic elements. So let's talk about hydrogen gas. Hydrogen gas is between a hydrogen and another hydrogen bonded together covalently. And since they share the same amount of electrons and they share the electrons equally, it's called a true nonpolar. So examples for this are all of your diatomics. So Brinkelhoff, bromine, chlorine, iodine, oxygen, all of your Brinkelhoff. And if you don't remember that, you can review that really quickly. Okay. And then electronegativity differences of less than 0.4 are what considers a covalent bond to be nonpolar. So if the electronegativity difference between the two elements is less than 0.4, then it is considered nonpolar. So here's a visual of nonpolar covalent bonds. So over here you can see that two identical atoms will share the electrons right here, and there's an equal sharing, which means there's no partial charge, no partial negative charge. Okay, polar covalent bonds. So this is when two atoms with differing electronegativities share electrons. So the more electronegative atom will have a greater attraction for the electrons and have a slight negative charge. So the more electronegative the atom, the higher the tendency to gain an electron, and therefore it will have a slightly negative charge since it gains that electron. And then the less electronegative atom will be deficient in the electrons and it will have a slight positive charge. Okay. So this thing right here is wrong. Please ignore this. It should say that the electronegativity is between 0.4 to 1.67. So yeah, if you find the electronegativity difference to be between 0.4 and 1.67, then it is a polar covalent bond. So let's look at this. So this is water. You'll see that hydrogen has a partial positive charge because it has a lower electronegativity, whereas oxygen is highly electronegative. And therefore, since it's highly electronegative, it's going to attract electrons, and that's why it has a partial negative charge. So if you look at this chart over here, hydrogen is all the way up here, so it's not very electronegative, whereas oxygen is all the way to the right of the period, and therefore it has a very high electronegativity, and that's why it's able to attract electrons and have a partial negative charge. And since there's a partial negative charge on the oxygen, this allows for the molecule to be polar. If you look at HCl over here, hydrogen is also not very electronegative, so it's going to have a partial positive charge, whereas chlorine is highly electronegative, so it will attract those electrons and have a partial negative charge. Okay, so the bond type is the result of the electronegativity difference of the two atoms. So a difference between 0 to 0.4 is nonpolar covalent. A difference that is less than 1.67 and greater than 0.4 is polar covalent. And any difference that is greater than 1.67 is ionic. So technically, ionic bonds are actually polar because there is a partial negative, partial positive charge. But the thing is, they're actually like donating the electrons. That's why we don't call it covalent. So here's an electronegativity chart. So if you're having trouble like understanding what like an electronegativity difference is, you can look at this. So if you look at oxygen, let's say oxygen is bonded with another oxygen. This is oxygen gas. That's going to be 3.5 minus 3.5, and the difference is 0. Since the difference is 0, it's nonpolar covalent. If you look at something else, like very similar atoms that aren't the same, so let's say a hydrogen is bonded with, I don't know, bromide. You're not going to see that, but the difference is 0.1, which makes it nonpolar. Okay, now let's look at a polar covalent bond. So let's look at water. You have oxygen 3.5 minus hydrogen 2.1. That's 1.4, which is a large difference, which makes it polar. Okay, now let's go over VSEPR, molecular shapes, and polarity. Okay, so what is VSEPR? VSEPR stands for valence shell electron pair repulsion. So make sure you remember this for your test because you're probably going to be asked what it stands for. So what is VSEPR? VSEPR allows us to determine the shape of the molecule, and it is based on arranging bonds to minimize the repulsion of electrons around the central atom. Okay, so here's a quick review. And this is a very important chart, so make sure you have this memorized. For Chem Honors, you don't need to know the 5 group and the 6 group, so you just need to know these 5 shapes. You just need to know linear, trigonal planar, bent, tetrahedral, and trigonal pyramidal. Okay, also this is a very good chart, so if you want to understand like electron groups, lone pairs, and what they look like, you should definitely refer to this chart. Okay, the first shape is linear. So linear electron geometries occur when there is no shared electrons on the central atom. So there can be at least 2 atoms that are bonded together, or sometimes there can be 3 atoms that are bonded together. Wait. Oh, that's a typo. Okay, yeah, so there can be at least 2 atoms that are bonded together. There are no lone pairs. So what lone pairs mean is like, let's say there were 2 lone pairs on top of the central atom. That would be an unshared electron. And in a linear shape, you can't have these lone pairs or else it's not linear. And logically, if you think about this, since electrons have repulsion, if you had a lone pair, the other atoms that are bonded like this will start to shift down because of that repulsion on the electrons. And when they shift down, this doesn't cause the shape to be linear. It causes it to change, and the angles also change. But in this case, when it is linear and there are no lone pairs, the atoms will just rest straight like this because there's no repulsion that's causing them to go wonky. So the bond angle is 180, and that's just because it's straight. I'm pretty sure you did like an online lab that told you to look at the molecular geometry and the electron geometry. Basically what the difference is, molecular geometries is when you're looking at it like with just the molecules, so kind of like this. Whereas electron geometries is when you're actually like looking at the molecules, but you're also looking at where the electrons are. Okay, the next shape is trigonal planar. So this is when 2 atoms bonded to a central atom with no unshared electrons are on the central atom. So this means you have your central atom and you have 3 atoms bonded to it. So for trigonal planars, there are no lone pairs, which means the central atom does not have extra electrons. And since there are no lone pairs, the bond angle will be 120. Okay? So the molecular geometry is trigonal planar, and the electron geometry is also trigonal planar because there's no lone pairs. So this is what it should look like. The next shape is bent with 1 lone pair. So this is when 2 atoms are bonded to the central atom with 1 unshared pair of electrons on the central atom. So that means there's 1 lone pair. And then in this case, the bond angle is also 120. In some cases, it will be different, but that's just something that you'd have to ask your teacher. And if you look at the molecular geometry, this is bent, right? But if you look at the electron geometry, when you're actually looking at the lone pairs on top of that central atom, the electron geometry is a trigonal planar because this shape that it forms is the same shape over here. Okay, so yeah, this is your molecular geometry when you're not looking at the lone pairs, and this is when you're looking at your lone pairs. Okay, our next shape is bent with 2 lone pairs. So this is when 2 atoms are bonded to the central atom with 2 unshared pairs of electrons on that central atom. So that means there are 2 lone pairs, and the bond angle is 104.7. The molecular geometry is bent, and the electron geometry is tetrahedral. We'll go over tetrahedral after this. But again, the molecular geometry looks like this. It's the same as the previous one. But in this case, there are 2 lone pairs, which causes more repulsion, and therefore the bond angle is smaller when there are 2 lone pairs compared to when there are 1 lone pair. This is because of the electron repulsion. So a very good example of a bent VSEPR shape with 2 lone pairs is water. So you can see how there are 2 lone pairs on top of the oxygen, which causes the hydrogen atoms to shift downward and bend. Okay, our next shape is trigonal pyramidal. So trigonal pyramids form when three atoms bonded to a central atom have one unshared pair of electrons. So that means there's one lone pair. The bond angle is 107.5. The molecular geometry is trigonal pyramidal, and the electron geometry is tetrahedral. So if you look at this is the molecular geometry. You have your central atom, and you have three atoms around it. But what causes this shape to not be the same as a trigonal planar is because you have that lone pair on top, which causes all of the atoms to shift downward to leave space for the lone pair due to the repulsion. So just make sure you remember this shape. Okay, and now we're going over tetrahedral. So a tetrahedral is formed when four atoms bonded to a central atom have no unshared pair of electrons on the central atom. So that means there are 0 lone pairs. The bond angle is 109.5. The molecular and electron geometry is tetrahedral. So if you look at this, you'll notice that the bond angle between everything is the same. Each atom has the same bond angle, and there are no lone pairs. So polarity. Polarity is based on the electronegativity differences. Polarity of molecules depend on the nature of the covalent bonds of the molecule. And you can use the VSEPR theory to find out the polarity of a molecule. If there are no polar bonds or the molecule is symmetrical, which means there are no lone pairs, the molecule will be nonpolar. So if you look at this, tetrahedral, there's no lone pairs, and it's nonpolar. And why is it nonpolar? Because there's no room for repulsion in the sense that, sorry, I said that wrong. There's not a big electronegativity difference where there can be temporary dipole moments, and we'll go over what that is. So just remember the symmetrical shapes are linear, trigonal planar, and tetrahedral. So it is polar if there is an unbalance of polarity. So we're going to go over this. So this is carbon dioxide. If you look at this, you'll notice that the shape is linear, right? So this is linear. And since it's straight, it's symmetrical, and therefore this is nonpolar. Okay. This is water, H2O. This is bent with 2 lone pairs because you can count 1, 2, and then you can also see it's bent. And you'll notice that this is polar because over here has 2 pairs of electrons, and then the hydrogens have to shift downward due to the repulsion, which means there's a electronegativity difference, and there's an imbalance of charge, which therefore makes it polar. Okay, and this is methane, CH4, and this is a tetrahedral because there are 4 atoms bonded to a central atom. They all share the same shape, and they all have the same bond angle. And therefore, since it has the same bond angle, this is symmetrical and therefore nonpolar. Okay, so let's go over intermolecular forces of attraction. So you can abbreviate this to IMFs. So intermolecular forces are forces that hold solids and liquids together. So if you look at this diagram, the IMF is what holds these 2 molecules together. Intramolecular forces are forces that hold atoms together to form bonds. So intramolecular forces are strong. They are strong forces. and they include ionic bonds, metallic bonds, and covalent bonds. So the intramolecular forces are like within the molecule, holding the molecule together, whereas intermolecular is what holds other molecules together. So intermolecular forces are much weaker than intramolecular forces. So what exactly does weaker mean? When we say like an intermolecular force is weaker, that means the energy required to overcome the force is higher. You need much more energy to overcome the force. Okay, and when we're talking about IMFs, you never say breaking the IMF. So you can't say the energy needed to break the IMF. You cannot say that. It's actually the energy needed to overcome the IMF. So you cannot break IMFs, you can overcome them. So on your tests, when you're told to write about IMFs and like energy, you want to say overcome the IMF, not breaking the IMF. So the first IMF is London dispersion forces. So London dispersion forces occur because sometimes the electrons in a nonpolar molecule will get lopsided and make one end negative. So the end that is negative can induce a duple in another nonpolar molecule, and this causes a temporary duple moment. So if that's hard to understand just by like reading the words, you can look at this diagram. So notice how these are the same molecules, okay? These are both iodine atoms, and it is nonpolar, right? Because the electronegativity difference is 0. So you can notice how there's a partial negative and a partial positive charge, and that's due to the temporary duple moment. So London dispersion forces are the weakest IMF, and molecules with a larger atomic radius will have a stronger London dispersion force. So the larger the molecule, the more polarizable it is. So on your test, you may be asked to compare two molecules, and they'll ask you which one has a stronger IMF. And when you're looking at it, you're going to be like, oh, these are both London dispersion forces since they're both nonpolar. So what you're going to look at is you're going to look at the atomic radius, and whichever one has a greater mass, a greater atomic radius, or greater molar mass, will be your stronger IMF. So London dispersion forces occur in nonpolar molecules. Our next IMF is duple-duple forces. So duple-duple forces are a type of interaction between a duple and another duple. So what is a duple? A duple is a bond or molecule whose ends have opposite charges. So a duple is when you have a partial negative, partial positive charge. So duple-duple forces exist between neutral polar molecules. So if you look at this, there's a duple-duple force between your hydrogen and your chlorine, because chlorine has a partial negative charge due to its electronegativity, and hydrogen has a partial positive charge. So if your electronegativity difference is greater than 0.4, it's likely you have a duple-duple force. Okay, and then a special type of duple-duple force is hydrogen bonding. So hydrogen bonding is our strongest IMF that we're going to go over. So this is a very strong IMF. So hydrogen bonding occurs when hydrogen is bonded to a highly electronegative element, which includes nitrogen, oxygen, and fluorine. So when hydrogen is bonded to either nitrogen, oxygen, or fluorine, this is a hydrogen bond. So it's a very strong IMF, and therefore the boiling point of elements with hydrogen bondings is extremely high. So let's go over why your boiling point increases with IMF. So we know that as the IMF increases, the energy needed to overcome your IMF also increases. And what is heat? Heat is energy. So as energy increases, you need more heat, or more heat is produced. So stronger IMFs need more heat in order for their bonds to be overcome. And that's why we say that the stronger the IMF, the higher the boiling point. So let's look at this. This is our hydrogen bonds, and it occurs between a partial positive end and a partial negative end. So hydrocarbons, you don't really need to know much about these. You just need to know that hydrocarbons are saturated when there are single bonds, and they are unsaturated when there are double bonds. Okay, properties impacted by IMFs. Vapor pressure, as the attraction gets stronger, vapor pressure decreases. Boiling point, as the attraction gets stronger, boiling point increases. Surface tension, as the attraction increases, surface tension increases. Make sure you understand how to explain these. Okay, and then from weakest to strongest, you have your van der Waals forces, which is your London dispersion forces. Then your duple, hydrogen bonds, and then ion duple. You don't need to know about that. Okay, and that's all. Good luck on your test. Bye-bye.